Hi everyone. In this video, we're going to talk about exponential growth and decay. So here we have the general form of exponential model is a equal a0 times e to the power of kt, which t is the x-axis, a is the y-axis. So a equal a0 represent the initial amount. So this is how much you starting, okay? Times by a, a is natural number, which is 2.71 to the power of kt. K is the dilation factor, and you have the t here. All right. Now, um, if you have k is bigger than positive number, then you will have growth. So this one is for k positive. Otherwise, if I have k negative, then my graph will go upside down. So my graph will go like this. So this is so you start from I0 and you go here. So that is when you have a reflections in the y-axis, it will go like that. Just keep in mind that exponential model can be in different form, depend on what questions and the curriculum that you're learning as well. So, for example, I could have y. It's a similar form, so y equal a is y, a0 is initial, times by b is the base to the power of t. So think about t is the x-axis, I is a y-axis, and here you have I0 is initial, so I0 here. So if B is positive, bigger than 1, then you have growth, okay? Otherwise, if you have I0 here, and if you have B is less than 1, and B is always bigger than 0, okay, that's the base, then your shape will be like that. That will be decay. So we can use either this form or this form. All right. Now we're going to do some example together of see how we apply. And all of these questions, I will use the second form because the second one is easier, like faster to use. Okay, A0 times B to the power of T. Now, here they say, what is the generation time of the bacterial population that increased from 5,000 to 100,000 in 4 hours? If we think of a diagram, so T is the time, okay, that's T, and A is the population. So population is A. Now, the initial population is 5,000, and they're telling you that after 4 hours, so after 4 hours, it reached 100,000. Okay, so you do have a point here. So eventually, when you link them together, it looks like that. So this is growth. Now, when you do this kind of question, your first step, you need to find out what is the equation, what is the I0 and what's the B. So I0 is the initial. So we know I0 is 5,000. All right. We just need to find B. And in order to find B, we just need to know T and A. So technically, we need to know a point. And they do give you the point in the question. So this point is 4 and 100,000. So I sub it in. So I have 100,000 equal A0 is 5,000 times B and T is 4. Okay. Then I divide it by 5,000 on both sides. You would have this one 20 equal B to the power of 4. And to carry off power 4, you fourth root the other side. So fourth root of 20 equal B. I can use my calculator to know approximately what it is, but I like to keep an exact form for now. So therefore, the equation that I have for this model will be y I equal 5,000 times b is 4 root of 20, that's the base, yeah, to the power of t. All right, now let's back to the questions. They want you to find the generational time. So what does that actually mean? The generational time is the time it takes to double the initial amount. the initial population. So think about if the initial population is 5,000, double 5,000 is 10,000. So they asking you, if it go up to 10,000, how long will it take? That's the questions, okay? So what you do here is technically you know the population is 10,000. So you have 10,000 equal 5,000 times 4 root of 20 to the power of t, and we solve for t. So we divide it by 5,000 on this side. You will have 2 equal 4 root of 20 to the power of t, and then you carry up 4 root of 20, you log it. So you log of whatever the number here is, log 4 root of 20 of 2 equal t. Okay. Then I would go to my calculator and I want to do log a of 4 root of 20 equal to up to like that. And that give me, if I control enter, that give me 0.925 hours. And if you want to convert to minutes, you're going to time this by 60 to convert to minutes. So it will take me 55.53 minutes to double the population. All right. So So the answer for this question, so here it gives me 0.92 equal t. So time that's in hours. And then if we time by 60, that gives us 55.3 minutes. Okay, so that's the generational time. All right. Now we do another example, but this time we're going to do a decay model. Here they said after 1,000 years, the sample is have decayed to 64.7 of original mass. Find the half-life. So similar to generational time, half-life is the time it takes to half the amount, half the initial amount. All right. So what I have here is if you think about the graph, you do have T as a time, I is the population. Um, After 1,000 years, the sample reduces that much. So think about A0 at the start, right? And I know that it's decay because it's decreasing. Now, it take 1,000 years. So think about 1,000 is the time. After 1,000 years, you only have 0.64.7%, means 0.647 of the initial mass mean A0. So 0.647 of A0. That's what I don't know what A0, but 64% of that amount. Okay. Now, they say for the half-life, the time it takes to halve the initial amount. The initial amount is A0, so half of that will be 0.5 A0. So we want to know how long they take to get to 0.5 A0. So we pretty much do the same thing. We're going to have model A equal A0 times B to the power of T, and we don't know A0, right? But we can find B if we just substitute a point T and A0. So this point here we have here is 1,000 and 0.647 A0. So we sub it in. So A we replace at 0.647 A0 equal A0 times B to the power of T. T is 1,000, okay? Then we solve for B. So what we can see here is A0 and A0 is technically go away. Then we want to carry up 1,000. So we fourth root that. Oh, sorry, 1,000 root that. So 1,000 root of 0.647 equal B. Okay. So whatever that is, I can put that on my calculator to know the approximate solution, but I just leave it for now, right? Because I want to leave an exact form. So therefore, the exponential model will be y a equal a0, I don't know, a0 times b is the base, which is that number, whatever that number is, 1,000 root 0.647 to the power of t. Okay. Now we're answering the question. So when I equal 0.580, we want to find the time. So we're going to replace I at 50% of I0, and we're going to solve for t. So we let I equal that. Okay. All right. So we have A0, we cancel on both sides. Okay. Then to solve for t, you just need to log of whatever the number here to the other side. So you do log 1,000 of 0.647 of 0.5, and that will give you t. And from here, I just put this on my calculator. So I have, I think log, and then I do for 1,000, 0.647 of 0.5 here. And that gives me 1,992 roughly. So that's the time it takes to half initial amount. So 1,592 years. It's a long time. So you know that when it here 1,592 years, then it get half of the original amount. We call that half-life. All right. Now we have a few more example. Feel free to pause the video and work on this question first before see the solution. Now here another question about population. They said to you that it was 8,000 at the beginning of 2007, and then 15,000 at the end of 2014. So if you think about the curve, so t is the time, okay, the year, the number of years, and population, let's call that I, just like similar previously. So initial is 8,000. So we're going to assume at the beginning of 2007, that's where t equals 0. Okay. Then 15,000 is when the end of 2014. So think about at some point here, it's going to reach 15,000. Okay. And if think about when t equals 0, that's the beginning of 2007, right? So 2007, t will be 0. So if you do 2014, t will be the difference between those numbers, which is 7 years later. Okay, but remember, we're talking about the beginning. So the beginning of 2007. So this means the beginning of 2014 will be t equals 7. But the question telling you that it was the end of 2014. So this means if at the end of 2014, it means you do have another year, right? So the end of 2014 is basically the beginning of 2015. So you would need to have increased that one more year. So t equal 8, okay? So here you have 8 here. So it takes 8 years to reach 15,000. All right. Now we can find the model, and then we can answer the questions. Now, so we're going to call the model the same thing, is I equal A0 times base of half t. A0 is 8,000 times base of half t. Now they give us the point, that point here, we can sub it in and find B. So A is 15,000 equal 8,000 times B to the power of 8. Then divide by 15,000 on this side. So cancel out. So you have 15 over 8 equal B to the power of 8. Right? Then to get rid of A, you A root the other side. So A root of 15 over 8 equal B. Okay, so you will have equation y A equal 8,000 times A root of 15 over A, the power of B, the power of t, sorry. Now you can answer the questions. The population at the end of 2016. So this means at the end of 2016, 2000, at the end of 2014 is t equal 8. So this means you just need to do 2 more years. At the end of 2016 will be 8 plus 2 is 10. So think about 10 years here. If you keep increasing, they want to know, if I expand the graph, they want to know what is a new population there. All right. Basically, we just substitute 10 in. So we have at t equal 10, a will be 8,000 times 8, 15 over a of to the power of 10, like that. And then you just work it out on the calculator, whatever that is the answer. Okay. Then for B, okay, for B, what year we take to double of 2014? So you can see 2014 is 15,000. Okay, so double 15,000 is 30,000. So you have 30,000 equal, so that's the A value here, equal, and you let the whole equation equal 8,000 times a root of 15 over a to the power of t. And basically you're just solving for t from here. So you divide it by 8,000 to this side. So 30,000 divided by 8,000 is 30 over 8, which is 15 over 4, equal a root of 15 over 8 to the power of t. Then to get rid of this number, the whole constant, we log on the other side. So log of 8, 15 over 8 of 15 over 4, that gives you t. And you just put that on the calculator, you get the t value, okay? And whatever that is, you add in from 2007, that will be the year that we want. All right, the last question I want to talk about is this question here, which is a bit more challenging. Now, if we read this, there were approximately 10 times as many red kangaroo as gray kangaroo. So what that means is red. So you have 10 times of gray. So 10 times of gray kangaroo equal a red equal the number of red kangaroo. Okay, so it's the initial amount. So we're talking about initially, you have, more red than gray. Now they're telling you that if the population of gray increase at 11% and red decrease at 5%. So let's think about the model here first. If you think about t is the time, okay, and this is the population, let's call that the y value or whatever you want to call that. Now, if they say gray, so gray, let's call that G0 here is initial. So I do have population here. Now, gray kangaroo increasing, so you have an increased graph, all right? Now, G, the general form will be G equal G0, which is the initial, I don't know the initial, times by b to the power of t, okay? T is the time. Because it's increased by 11%, this means the base here, think about you have 100% initially, you plus 11%, that gives you 111%, which is 1.11. So that's the base. So you know that the equation for this model will be G equal G0 times 1.11 to the power of t, right? Then think about, similarly, if I have to do for red is decreased by 5%. So red initially is bigger than G0. So RO is somewhere here. There's a 10 time gap, and red will decrease like that. Okay. So the general form for red equal R0 times, and because you decrease by 5%, think about you have 100%. And if you minus 5%, you get 95%, which is 0.95. So B is 0.95 to the power of t. All right. Now, that's how we interpret the question. Then they say that how many year, sorry, find out how many years must is elapsed before the population are reversed. So what that means is you can think about initially you have more red than gray, right? After a certain amount of time, you can see the red decreasing, the gray increasing. So they're telling you that after some year here, that's what we're looking for. How many years they take for gray now become 10 times of red. So because at the moment, gray times red with time 10 will give you red. So how many years did it take for the red? Now time by 10 to give you right. So in other words, we're saying that at this time, the gray population, okay, gray population is 10 times of the red population. So gray population is that is G0 times 1.11 to the power of T. Okay, and we have 10 here time. The red population is that time R0 0.95 to the power of T. And we're solving for T from here. So how do we solve for T? Here they give you R0 is 10 of G0. So R0 here, you're going to replace that at 10 of G0. Okay, so you have G0 times 1.11 to the power of T equal 10 times, replay this at 10 G0 times 0.95 T. So you have G0 cancel out, the normal, and you can solve for T from there. So 10 times 10 is 100. 1.11 to the power of T equal 100 times 0.95 T, all right? Then to solve for T, we're going to put D together. This is times, so we divide 0.95 T to the other side. So we do 1.11 to the power of T divided by 0.95 to the power of T equal 100. So we can combine them, okay? So this one we can be written as 1.1195 to the power of T equal 100. And we can solve for T by log it over. So T equal log of 1.11 over 0.95 of 100. And then you can put that on the calculator to get approximately what's the solution for this. So that's the answer. How many years, whatever the year it takes, that is how many years it takes here, the T value here, for the population to be reversed.